is this number? What is the meaning? So let's assume that alpha, say beta, beta is of the form for f1 dy dc plus f2 dc dx plus f3 dx dy. And that's the two form on say let's say on maybe some open subset, but let's say that it's defined on the whole of R3 or some open subset of it. Let's move functions which we the smooth functions f1. And we can also think of f, where we plug all of them together, so f1, f2, f3, as a function that eats a point and spits out a vector, and we can think of that function as a vector field. As a vector field on R3, or precisely on an open subset of R3. So we have just like some part of our space, and then at every point we have like a vector, and that vector field might change. So we have like some changing vector field in R3. We might restrict that vector field to some surface in R3, but for the moment that's not so important. But what we can do is that R dB and CD and U be a rectangular region. And then let's denote by Tx, xy. Be just dr, dx, and xy, and ty, xy. The two vector fields. So essentially, what you have is like that rectangle, and you might like consider that in space like that. And then we have like at each point of the rectangular, we have like something in x direction and something in y direction. And what we do now is we want to talk about the normal direction. So what we do is we take the the product of the two vectors. So we take this vector, and then we take the right hand rule. We take like the product, and then we get a vector that points outwards of the surface. So what we get is then an n of x and y, which is tx point, and then we take the cross product. It's the normal vector at the point. And we need a little bit more notation, namely write Tx, which is a vector field, as we need the components of that as t1, t2x. These ones are the components of Tx, which are in itself functions again. And of course, similarly for Ty, and because they're the components, what we then have is then if you have dx, which is just a constant one form in the x direction, and you plug in the vector field in tx and x direction, like given by the in x direction, but like given by the region, what you get is just the first component, tx. Similarly, ty, and so on. So these are like really the components of this vector field, Tx. So let's calculate like this integral. So where was beta? So beta is this guy here. So we need to evaluate it. So what we get is that it b equal over c of d of beta evaluated here, and then we have to insert tx at that point, ty at that point, and then integrate dy and dx again. So that's the definition, just writing tx and ty for this dr, dx, and dy. So it's using this definition that we had like in the upper line of tx. So that's the definition. And now we just plug in our values. So a, b, here we don't change anything. And now we just plug in this particular vector, or this particular two form. So it's f1 dy dc. So it's f1. Let's maybe I go very slowly for the first part. So it's f1 evaluated at that point here. And now we have to put it as a dy dc. So it's dy dc and dx xy dy xy. And then all of that other stuff comes in here. So what this expression here is, we get two contributions by using this wedge product, by the definition of the wedge product. So what is happening is that we have dy is hitting the first vector, but if dy hits the first vector, by this formula here, it just gives you the second component of tx. So what we get here is that tx of the first vector field times the third component of the second vector field. And then we, by the wedge product, we get minus sign, so that these two interchange. So what we end up with that we change these numbers up here. So it's tx, the third factor, and here 2y, the second vector. If you do the same calculation, what you end up with the upper part, T3 x T1 y minus T3 y T1 x plus F3 T1x T2y minus T1y and then we have to integrate all of that stuff over dy and dx. But now you look at these terms like for a while. You can do that while I erase the lower blackboard, and you try to find something that you know. And you want to write it like in something that you know. So what you see here is like you have F1, F2, F3 here. So that looks like times something. That looks like a dot product. And then if you look here, if you look very careful, what you see is that these ones are the elements of the cross product of these two vectors, of tx and ty. So it's like exactly the components in the right order. So what you see is that you can write all of that mass in a nicer way as f, which is the vector field, times the normal vector field, and that's really here the dot product, and then we calculate dy dx. So that's a nice formula, definitely nicer than the second one. And let's say something that you already know, or hopefully you recognize these kind of things. Maybe this one is the classical surface integral over the vector field. Capital F. And that one calculates in physics language, that would be the flux of the vector field F through the surface, or through the rectangle. So what you can imagine is like you have like some vector field that flows, let's say, like for example, that's like the flow of water or something. And then based on that, you put like a very small, so that's like everything in 3 dimensions. So what you put in is like some kind of like a sheet of paper or something that it's a measuring device. And then you measure how much of the fluid is flowing through this rectangular version. And that's exactly given by this integral. It measures how much of the fluid is going through a particular given area element. So, like this a bit lengthy calculation was showing you that, like, if you have a particular two form, which is in this case related to a vector field by this formula that it's like a nice combination of the dx and dy's, then what you end up with is like just something that you know from the classical version, namely that it's a classical surface integral that you might have learned in some other courses. And you might, like someone asked me in the break, like, why do we have actually a two form to be antisymmetric? So why do we require that there's a minus sign? And if you look at what this gives you is this minus sign is essentially these minus signs here. If that would be symmetric, if like for whatever definition that would be symmetric, then you would get a symmetric version here, tx and ty. But of course, if there would be a plus sign here, then you would not be able to recognize the coefficients of the normal vector, which is defined as the cross product of the two vectors. So that's why we want to kind of build in, or that's one of the reasons why we want to build in this minus sign in the definition of the true form, is that that they correspond, these integrations, for example, correspond to something that we know. If you would have a plus sign there, then who knows what that expression on the right-hand side is. That it's like some version of like these tangent vectors, and you calculate something, but the something is like no longer meaningful. Only if you require that it's like antisymmetric, then it becomes the cross product of these two vectors, which gives you then a normal vector. And then you get like some like physical explanation of what you actually integrate and what you calculate. So that's one way to see why this minus sign might be important. Okay. What I would now like to discuss a little bit more in detail is how the integral relates to the differentiation. So that's usually very important. So it's a fundamental theorem in calculus, which tells you that the integral is the antiderivative. And similar results, you have certain results if you integrate, for example, you have like the Stokes and the Green's theorem that tells you that if you integrate certain things over a surface, that you can like integrate that, reduce it to like boundary terms, for example. So the one-dimensional case, or the degree 1 case, would be you have the integral of a function of the one form which is exact equals to just f evaluated at the endpoint. So we can think of that as a very one-dimensional integral, namely we take the boundary points of the curve, which would be just the endpoints, and then integrate f over that. So it's like a discrete integral, but like it's just like saying that this right-hand side is taking only the boundary terms of C into account. And we have a theorem which is Green's theorem, which says that if you have U open, some open subset of R2, and alpha a two form on U. And suppose that we have some rectangular region. And we want to assume that R is injective. So we don't want like that this region is like a rectangular and then you fold it and it intersects each other. So we want it to be injective and such that the Jacobian is positive. So you take the Jacobian metric, so you take the partial derivatives of all of that, and you take the Jacobian matrix, and then you calculate the determinant, and you want that this one is the determinant of the Jacobian. It gives you a positive number. And we would like to denote the boundary and that dr be the boundary curve of R, which we oriented so that R lies on the left. On the left. So the picture just like a lot of words for, so you have that to be R. And then you would like to have your boundary curve. You have two choices. You can either walk around it like this, or you walk around like this. That's the two choices that you have for the boundary curve. And we would like to walk such that R is left. So we walk up here and then look to the left, and we want R to be here. So we walk around. So we walk around the boundary in such a way that if you look left, then you see R. So that's the content, and then we have the following result, which is that the integral over R over d alpha. So we have alpha as a one form, we take d of that, we get a two form, and then we can integrate that two form. And the nice thing about this is that it's related to this line integral about alpha. And that's essentially, if you think about it in this version there, this one is equivalent to Stokes' theorem, which you might have seen already in some course, which is that the integral over the curl of some vector field times n, so like integrated over dA, equals to over a certain line integral. That's essentially the same content, or like this special case of this theorem that we have now. So it's really like really important, like to go through it. Like we have here alpha as a 1 form, so d alpha is a 2 form, so we can integrate it over a 2-dimensional object. And what we have here is alpha as a 1 form, dr is a certain line, so we can also integrate them. And then, like the nice part about this is that both of these ones are equal. So if you can see that in some way, means that if you take d of alpha and integrate, then that's the same thing as like taking the boundary and then integrating over alpha. Okay. Let's have a look at the proof. So because we have some 2-dimensional object, the alpha is like a the 1 form in 2 dimensions. We can write alpha as alpha 1 dx plus alpha 2 dy, as you have seen now. For some smooth functions, and then we have d alpha being the same thing as d alpha 1 which dx plus d alpha 2 which dy, and now we rephrase that as, then this one is d alpha 1 in the y direction, dy which dx is a certain contribution from the x direction, but this is killed by the space product with dx. And here we have the same thing, but now we only get the x direction. So what we see now is that we have to turn around here the summands again, and then we can combine of these two forms. So what we have is alpha 2 minus d alpha 1 over d1 dx dy, which is, by the way, the same formula that we got at the beginning of the class. So let's be very straightforward and just plug this formula in our definition for the integral and see what happens. So we calculate now what this term is, and then we get that it's the integral over a certain expression, and then we have here d alpha dx and y, and here we have dr dx dy, and then we integrate dy and dx. And using this formula up there, what we obtain is that it's minus d alpha 2 over dx, and then evaluated rxy, plus sign, minus d alpha 1 in the y direction. So that's the first part. And then we have to evaluate dx, dy on these two vectors. So what we get is dx on these two vectors. So dx dr over dx times dy over dr over dy minus, and then really turn around dy and dy in the x direction. Yeah, so assume that we can write can always write these two functions, because it's like takes values in R2. We can always have like component 1 and component 2 of that. And then we can calculate this expression, which would be just the first element, dr1 over dx. And similarly, this one would be a dy of the second component. So what this term here in total we've calculated is dr1 over dx, dr2 over dy, minus dy in the first element, and then dr2 over dx. And if you look at this expression for a little bit, what we end up with is that this one is the determinant over where we take dr dx. Here we have the vector dr dy. So in total, what we get is now times the determinant of this matrix. Dx, dy. Okay, so what we see now is that that here we have always a function r, and here we have always a function r, and we have the Jacobian here. So we can use the substitution formula for surface integrals to substitute the r and get that out, to get an expression where we integrate just like the normal surface integral over the image of r, and then we have here just the unsubstituted values. Dxy. you might have seen an integral like this before, and that's, we can calculate using the ordinary Green's theorem. For surface integrals, which was exactly about like terms like this, to calculate it as the integral over dr of the boundary of alpha 1 dx plus alpha 2 dy. So that's just like really the ordinary Green's theorem. And here on this left-hand side, it's the normal functions and the normal integration. So dx and dy just stand for the normal integration and not for the differential forms. But of course, this expression here is defined to be the same thing as like the line integral. So really as differential forms, it's also nothing than just dr d alpha. So the proof is a bit longer, but what I would like to emphasize here is that we have two elements that come into the proof. The first one is that we have some kind of substitution law, which then involves the Jacobian and the determinant. And the determinant comes in from the play that we have this wedge product, right? So here it was really the wedge product of dx wedge dy that gives us the Jacobian of R. So this wedge product is really there to get us the determinant, and the determinant is then used to transform the integral that we calculate into an integral that we know already, and then we apply some ordinary theorems that we know to the result, and then get something that we can write back in terms of the original forms. So it's really like usually two elements that go in these kind of proofs. The first one is that we have some results in calculus that we would like to generalize. Here it's this kind of Green's theorem, and then you combine that with some natural transformation laws under change of coordinates or some kind of results like that to actually calculate these terms. Okay, don't know if that makes sense to. Yeah, I think it's a good moment to stop here. And then next week we talk a little bit more about how to integrate over multiple patches. So we have like our surface, how to we can patch that together with rectangle elements and then cover our whole surface. So that will be a subject of next week. Then I wish you still a good evening. Come home like relatively safe. Don't get too wet. And then see each other next week.
first like a little bit confused about the definition. So in differential forms, do I take dx and dy as a kind of like a mapping, or kind of like so dx and dy is different from the dx and dy in integral, right? It's more vague because you have to sometimes you write like dx but you want like it's vector, so it's kind of like a mapping.
Yeah, so that's the best way to think of that. It's like dx, dy are really like elements that each tangent vector and gives you something. In the integral, it's just like, yeah, it's just like some symbol, right? Like it means like just like denotes where you integrate in which direction, essentially. But there's no, like, essentially they are the same, like, because we can define like the integral of the one form, like the. You notice, like, essentially but if you see like alpha is like C is, for example, the constant, then like essentially it boils down to having like a statement that dt here as a one form, and this one is just like as a symbol. So that's a bit like maybe why you get confused, because here it's really like on that left-hand side it's always really like a one form. Here it's meaning as a symbol. So you can also see it like conversely that it makes sense now to talk about the symbol actually as a one form. That would be maybe one way to see it. And the way it is designed is like to get to the Jacobi. So that's like why we have this minus sign at the equation. Really like to make it have some connection with the Jacobi. I really don't like that. I think that makes it suggest that it's like the integration and you don't know which one is actually coming first. So really, I prefer to really write it down explicitly. You still have questions? But we talk about so that we have to first say what the integration yeah, like, so it's like continuous. Yes. Yeah, if you think of like that, like saying that like yeah, that you consider R to be the image for one thing. Yes. 它那个目标表到底是跟着那条 neighbor 有关系的。你只要但它那个目标表的话，还不如看一个。那个定义有上面表的知乎。没整。我在知乎上看到，应该看了，是在别人。That's why like没有two dimensions like没有包有包有。So that's like what we do. What we have to first say, how do you make sense of, like, say, for example, which is not covered by it's really like you can, for example, have like the sphere, the upper sphere. You can like make sense of that as a vector. But then we would also say that we want to kind of like sum up like we get from the second. And then we need to make sure that like the overlaps match and then get like the integration from the boundary. So that's like we will talk about next time. You say is the change of one of but union one why must be 你要去看这个 why 2 yeah by definition because just one means that it's yeah so sometimes we say the just like take the V1 into yeah, like one is also like it's it's a question of if you like it measures definitely how much alpha is changing. But of course it's not as simple as just saying it's like but it's also very hard to say what does it mean for one form, right? Like the one form needs to be like it would be very strange to say that the measure of the change of alpha would be just like typing alpha like a vector and then measure the change of that. Why would that be the change of alpha? So it's like, I mean, this one also, like the Z1 might change. So you measure. Yeah, but then the slide, like the slide, it depends on this. So this, like if you say like the 6v1, it means that like eventually what you reduce is like you reduce like one vector, right? But like we would like to, then it's really just like having a function and you measure the weight of that function. But it's not, what we really want is like, we want to measure as a one form how the alpha change. And that's measured into something. Yeah, like that's by definition a two form. Yeah, it's I don't know if I can give you better answer. If you really want two form, but it's essentially coming from the statement. If you like this one, it's like essentially giving you the justification that our definition was correct. Because it says like, yeah, that's a nice result that makes sense. Of course, you can define that one differently. But yeah, that's no longer like satisfying. Yes, so I heard you see that as a design, but there's also like some resorts that, for example, that characterize this map in terms of x-units. So that's like really a formula, right? We kind of like come up with this idea of it should measure the change of alpha in some way, and then we come up with the formula. But there are also certain things like that this one is the unique map which respects the likeness property and has some properties. And you can characterize this form uniquely. So there's like theorems also of that kind. So it's like, of course there's some design choice, but like financial assumptions on it, that neither is actually unique. Thank you. You're welcome. You still have a question? It's okay to ask a question like sitting here, so that's like really under a sheet of paper. But if you fold your sheet of paper, you have like something like this. So that's like the folding of the sheet of paper. And then you would like to say, what is the induced vector here? So you have like something that is here, and which is also curved. And this one here it's like denoted by the side. So it's essentially the same vector here, but like on that change of surface.